Hello, welcome to this NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to see Python as modeling and simulation tool. During this course of study, we will be extensively using Python as a tool for our modeling and simulation task. Okay. So, I thought it appropriate just to have some basic idea about Python and its libraries, okay, and have some idea about what do we mean by modeling and simulation. Okay. So, I expect that after the end of this lecture, you will be able to explain the role of modeling simulation in robotics. You will be able to understand the basic terminologies, recognize the importance of simulation before the real object, real robot deployment, okay, and understand how Python supports our modeling and simulation task, and Jetson Orin Nano as edge computing device and the booting process, and finally installation and execution of Python script in Jetson Orin Nano. Okay. So, initially I have divided this lecture into two broader segments. The first segment I am going to talk about the modeling and simulation, and then in the second segment I am going to talk about the Python as a tool for the modeling and simulation. Okay. Why do we need to model anything? Okay. It is always easy, okay, to make the changes, study the behavior of a robot before we actually make the robot. Okay. That is why the modeling and simulation are essential. So, once you are satisfied with your simulation and animation results, then you can go for the deployment of your control algorithm into your robot. Okay. So, modeling and simulation is the theoretical basis which is rooted in the dynamic system, computer science and the domain ontology. Okay. So, to define the modeling, basically it is creating approximations of the real world events system. Okay. So, mathematical model actually represents the robot's kinematics which we are going to study, and the functioning of human brain as an AI neural network architecture. Okay. And in simulation we are going to see how that model behaves actually. Okay. So, we are going to do the analysis of the model which we create. So, basically means we are going to draw conclusions, verify and validate the research and make recommendation based on the simulation, and then we are going to see the visualize how it looks like. Okay. So, modeling simulation for a simple robot, suppose this is my system, a robot is a system, I can make a simple model of that. Okay. And in simulation I am going to see the behavior. Okay. And analysis and visualization, for example, say I am going to see how my end effector trajectory changes with time. Okay. So, this is what I am going to do. Alright. System is basically defined as some entity basically, okay, or which we are going to study. Okay. So, there is a definition for the system by International Council of Systems Engineering, which says that it is a construct or collection of different elements, say people, hardware, software, facilities, etc., that together produce results not obtainable by those elements individually. Systems can be studied through the actual system versus a model, physical versus mathematical representation, or an analytical solution versus the simulation solution. Coming to the models, model can be classified based on how time is represented. So, we can have the continuous time system, okay, where the state variable changes continuously with time. Say here you have the continuous variation with time, okay, and they are often described using differential equations, okay, and they are very common for physical system analysis. Okay. The second classification is the discrete time systems, okay, where system state update at fixed time intervals, and they are well suited for the computer simulation which we are going to do here. So, this is the way you have the discrete time systems, okay, and these are common in digital control and Python based simulations. Okay. So, updating the robot position every delta t time, say in a map. Okay. So, that could be an example, and robot's actual motor velocity as is shown in a continuous state variable, that could also be example. Okay. Next, let us look at a model. So, a model is a physical, mathematical or logical representation of a system entity, okay, phenomena or process created to understand, analyze or predict its behavior. You see, our real systems are very complex actually. Okay, so if you want to mathematically analyze, you need to make certain assumptions and you need to simplify your system. Okay, so that is how we create our model. Okay, so your model should capture only the important features of the system. Okay, a model should not represent every aspect of the system. Okay, so it should be as simple as possible. Okay, it should represent only the aspect that affect the performance being investigated. Okay, so simplicity and that is easy analysis and simulation, accuracy, that is meaningful prediction, these are some of basic requirement of the system. For example, I can give you an example. Suppose I have a robot. Alright. So, although my robot is a flexible one, but with sufficient accuracy I can consider it being constituted by the rigid bodies. Okay. Many of our robot joints having friction. Okay, but to simplify our analysis we can do an assumptions, we can have the ideal joint without friction. Okay. So, different modeling approaches that are used depending on the problem being studied. So, we could have the mathematical model, we could have the computational model and we could have the data driven model. Okay. So, in this course I am using Python, as I said, is used to implement and analyze computational model based on the mathematical ideas. Physics based modeling, this modeling could be physics based, okay, it could be your finite element modeling or it could be the data based modeling. The modeling could further be the agent based modeling or it could be your aggregate modeling or you could have a combination, okay, combination, that is hybrid modeling which combines the multiple modeling paradigm into a single simulation. Okay. Model also differ how they handle uncertainty. Okay. So, the deterministic model have the same input always, produce the same output, whereas in case of stochastic model output may vary even with the same input. Okay. In deterministic model there is no randomness involved, whereas in stochastic model you have the randomness or noise. Okay. So, the deterministic model is useful for theoretical analysis, whereas the stochastic model are important for modeling say sensors, environment and the real world uncertainties. So, robotic systems often require stochastic model to reflect the realistic conditions. Okay. So, let us look at some of the basic terminologies. What do we do in the simulation? So, once I have got a model, okay, now in simulation we could or this model could be in the form of say mathematical equations. So, in simulation what we do, we try to solve those mathematical equations and try to see its behavior over the time. Okay. So, how that system behaves. Alright. So, case of our robot, we would be interested in seeing how the joint velocities change over a time, okay, or how the joint position changes over the time. Okay. So, that is what we do. Okay. There are many advantages as I spoke. We could have cost efficiency, safety, speed, flexibility if we do all these things before actually making the prototype. So, simulation paradigm, there are three principal paradigm. The first one is the Monte Carlo simulation which uses random sampling from the input distribution to calculate the output, okay, and of course it relies on probabilities to model the behavior. For example, it is a frequently used AI for reinforcement learning. Alright. Continuous simulation, here the system variables are continuous function of time, typically involving differential equations, okay, and they are used to model the robot dynamics. Alright. Similarly, we have the discrete event simulation. Here variable changes only at discrete points in time associated with the specific events. Most robotic simulations are time based, meaning system behavior is evaluated as time progresses. Okay. So, that is there, and in these simulation initial conditions describe the starting state of the system, okay, and the initial position or velocity of a robot joint, they are, it is the example say for your initial position, alright, or say initial velocity of your robot itself, alright. So, simulation results are highly sensitive to these initial conditions, okay, and different starting states can lead to very different system behavior, okay, even when your model is going to be the same. So, we need to take care of these initial parameters. Now, how this process cycle evolves basically. So, development process cycle consists of say a model phase, we make the model, then we have the code phase where we write the code either in Python or say C++, okay, and then we execute them, okay, and then we analyze. So, basically you have a model, you have a code, we execute and then we analyze, okay. So, this cycle is repeated until the simulation team is satisfied with the result, okay. 3 descriptors define the properties of a model or simulation, okay. These descriptors are basically fidelity, that is the degree to which the model matches your reality. As I said, we are going to make so many assumptions when we are coming from the actual physical system to our model, okay. So, the fidelity represents degree to which the model matches in reality. Then what is the resolution? Okay, the level of details in the simulation, that is what we call at resolution, and the scale, okay, the size of the overall scenario or events. Okay. So, we could have various attribute relationship and trade off, okay, that is fidelity versus resolution, fidelity versus scale, resolution versus scale, and so on. Now, once we have done, you have prepared your model, you have simulated your model, now you need to see, okay, was the model built correctly, okay. This is what we call as the verification, okay. And was the right model built? If we answer for this question, then this is what we call as the validation, okay. So, while it is a powerful tool, simulation has got important limitations, okay. Model may ignore the real world effect. I said we are making so many assumptions on simplifying our model, okay. Numerical error may accumulate over a period of time, and simulated environment may be less complex than reality, okay, because simulating a real environment is really a tedious task, okay. So, simulation should be viewed as a decision support tool, not a perfect replacement for the real world testing, okay. So, effective engineers mitigate these limitations by incorporating the real hardware into the development process, okay. What is role in AI based robotics, okay. So, in AI based robotics, the model serves multiple roles, okay. So, it provides simulated environment for training AI algorithm, it supports testing and validation before the real world deployment, and it enables safe experimentation with control and decision making strategies, okay. So, even data driven AI system rely on model and simulation during the development, okay. And so, modeling and simulation is a foundational skill that supports all advanced topic in robotics and AI, as we will be seeing these things in our further lectures. Okay. Now, let me come to the second aspect of this lecture, and that is on the Python. Okay. So, Python as a mathematical modeling language. Okay. So, as you said, we engineer refer models often as mathematical equations. Okay. So, Python allows these equations to be represented computationally, evaluated numerically, studied under different conditions. Okay. So, instead of solving these equations in paper, Python enables engineers to change parameters easily, observe how system behavior changes, and focus on understanding what is the relationship between these variables. Okay. Many engineering and robotic model cannot be solved analytically and require numerical computation. These things we have already seen. Okay. And these numerical computation allows engineers to study realistic systems that are too complex for the closed form solution. Okay. Python supports numerical modeling by enabling handling of vectors and matrices, okay. The position vector of the end effector and matrices, that is we have seen already the rotation matrices, okay, of the links of the manipulator, okay. Approximate solution to complex equations, repeated calculation over time, okay. And the Python is suitable for say motion modeling and the dynamic system analysis and sensor and signal modeling and many more activities. All these things we are going to see during the study of this course. Now, in AI based robotics, Python based simulation plays several important roles. For example, training and testing AI algorithm in safe environment, evaluating decision making strategies and simulating environment that are difficult to reproduce physically. Okay. Even data driven AI system rely on simulation for say the development, debugging and the performance evaluation. Okay. Modern robotic system often run models and simulation on embedded or edge computing platform. Python based model can execute lightweight simulation close to the hardware, support real time decision making and enable testing and validation directly on the robotic platform. Okay. This allow modeling and simulation to move beyond desktop computer and become part of the robot onboard intelligence. Okay. These all activities are conducted in our lab for various type of robots. Okay. So, this is the Jetson Orin Nano module which is there in our lab and on which we are going to execute the various program for this particular course. Okay. So, we are using this NVIDIA Jetson as edge computing device. Okay. And yeah, it has got various features actually and the various facilities. Okay. So, the Jetpack SDK comprises the Jetson Linux and the Jetson AI stack and the Jetson can perform platform services. Okay. So, the Jetson Orin Nano development kit used as the edge computing platform for all Python and ROS2 implementation in this course. Okay. And initially when we have to work with this one, we need to first configure for the initial boot and install VS Code IDE and set up the virtual environment with required package and run the Python programs. Flash the respective Jetpack SDK using one of the two methods, either of these two method you can use, that is SD card image method or NVIDIA SDK manager method. Detailed guidelines you can find in this link, and after initial boot we can install the Visual Studio Code IDE for writing, executing and debugging. Okay. So, here is the way we could do that. So, we can create virtual environment and installing a package as explained in this slide. I am not going much into details of it, you can go through this. Okay. So, as I said, Python it is an interpreted high level programming language developed way back 1989. It supports procedural, object oriented and functional programming paradigm. It has clear, simple syntax, programming typing, garbage collection. The core functionality of the Python is extended with packages that can be downloaded, installed and then imported. There is a very big online community available for this one. So, if you have any problem, one can always approach for the help. So, the Python ecosystem for robotics and AI simulation comprises of say a numerical core with various type of packages, data and input output for the visualization, say here pandas for the data and input output visualization, matplotlib, and then for the machine learning say PyTorch, robotic simulation, PyBullet, control systems, computer vision, OpenCV and RL and planning, okay, for this one. So, we are going to see some of the things in this course, as it is not possible to cover everything in this course. Okay. So, here is about the NumPy, that is the numerical foundation, and the NumPy provides the array a fast, memory efficient n dimensional array. It underlines virtually every scientific Python library. Okay. So, here is an example given for its representation, okay, for the robot joint angles. Then we have SciPy, that is scientific computing toolkit, and this SciPy builds on NumPy to provide high level algorithm integration, optimization, signal processing, spatial algorithm and statistics. Okay. So, these features are available through SciPy. Then the matplotlib is basically used for the visualization, for simulation and analysis. Okay. So, it is a Python's fundamental plotting library, basically used to visualize trajectories. Here the robot trajectories, the sensor data, robot sensor data, face portraits, the Bode plots which we use in the controls, and the real time the robot state. Okay. So, these are some of the features available. Then the pandas, the data handling for the robot experiments. So, the pandas data frame are the standard container for the tabular robot data, ROS bag exports, sensor logs, experiment results and the training data set. All these things can be done. Here is one example shown for your reference. So, the basic Python, if you look at the basic Python concept, okay, so we have the data types and variable. The data type categorizes the different types of data, and they could have the multiple data, say you could have list, tuple, string, sets, dictionaries, etc. And Python uses zero indexing with square bracket, and variables are used to store, access and manipulate data in our program. Okay. So, and we have the function and arguments also, and a function is a piece of code which performs something very specific, such as say compute underscore distance. This could be a function, or arguments, additional data required by functions to perform a task, such as say speed and time. Here is a small example given over here. For example, I am defining the robot name as mobile robot using a string. I am defining the maximum speed, say using a float, and I am defining time using an integer. Okay. Similarly, using list I am defining the sensor data, using the tuple I define the robot pose, and using the sets I can define the various objects. Okay. And here I am using the function, say compute distance, okay, which has the argument speed and time, and then you could have the calculation for that. Okay. Then we have various modules. Python uses modules to grip similar functions, say class, variable, constant, etc. in a .py file, and Python's math module also provides some standard mathematical functions such as say square root, right, sqrt, and constant, say pi. The operators, normal operators, say plus, minus and multiplication. Then we have the various relational operators, logical operators we have, membership operators we have. All these operators are available in the Python. Then we use various type of control statements. Okay. It could be if else, or say for, or while statement, break statement, or continue statement. Here again we have an example given. For example, I write import math, then once I have imported the math library, I can define pi, I can define sqrt, that is square root, and say here this is a data, sensor data, I define for the list class, then I can use say if statement. Alright. Similarly, I can write the if else statement, and then I can write the print statement. Okay. Similarly, in Python we can define the object, okay, and the object is an entity which contains data as well as procedures that operates on that data. Object, say robot1, has data, variable name, variables name, speed, and procedure functions such as move, status and all. And we can define class also. Okay. The class data type such as robot is just a template that defines attributes as well as the method. Okay. So, attributes, what are that? Variables in class of the object, and methods are functions in the class. Okay. Alright. So, here again you have an example given here. So, define your robot as a class. Okay. And similarly we can define move, status, and finally we can define say robot 1 as an object. There are other features, say inheritance, mechanism to create a new class that is based upon the existing class by adding new attributes and method on top of the existing class. So, that facility is there. For example, I can create mobile robot and drone, they are the child classes that inherit from the robot, that is the parent class, okay, as it is given in this example. So, I am creating inheritance, a mobile robot and the drone over here, okay. And then your polymorphism is the other feature. It allows us to define methods in the child class with the same name as defined in the parent class, and the same move method is different from R1 and R2 objects. Sample program using NumPy, SciPy, Matplotlib packages. Here I could show that. I have already discussed about this, and they can be used to simulate a robot moving in 2D environment towards a goal and determine how close the robot reaches the goal. Okay. So, from NumPy we have the robot data, that is the numerical arrays and the matrix operation. From SciPy we do the scientific and numerical computation using algorithm, and using Matplotlib we do the data visualization. Okay. So, this is how we import NumPy, and from SciPy, and then we import Matplotlib, and then we can define this. Okay. We can update the robot position with the path, compute Euclidean distance using SciPy, and plot robot path using Matplotlib. Okay. So, here say for a robot this is the goal position. So, I can plot the x position and y position and say this is the robot path which it is going to take. Okay. So, here is a code written for visualization of the robot path, and here is a code for updating of the robot position and compute the distance to goal using SciPy, this one. So, you may just practice these codes either say in Google Colab. So, conceptual bridge to hands-on robotic system, the tool introduced in this module forms the programming essentials for later robotics and AI experiments. The concept learned here will be reused when we are simulating the robot in virtual environment, testing algorithm before being deployed in the real hardware, and integrating AI capabilities using existing packages. Okay. The Python based modeling prepares, interpret, analyze the raw simulation, debug the robotic behavior logically, and transition smoothly from the simulation to the real robot. Okay. So, Python is a simulation powerhouse. It unifies full AI robotic workflow. There are core stacks tools available, okay, and we can even do the robot dynamic simulations we will be seeing a little later. We can have the inverse kinematic, PID auto tuning and all. Then we have the physics based environment is there, and ROS2 is actually bridges between Python simulation and the real hardware, and performance bottlenecks in simulation are solved by vectorization. Basically here we are trying to integrate the simulation with the actual hardware implementation. Okay. So, to summarize, the key takeaway of this lecture is that a model simplified representation of a real system. Simulation uses models to study system behavior, and modeling and simulation actually reduce our risk, cost and development time, and the Python enables practical, flexible and repeatable simulation. Okay. And the use of packages which I have talked about, either NumPy or SciPy, okay, these packages allow us to quickly deploy the numerical algorithm to a robotic system. Okay. So, with this I would like to close. Thank you very much.